It's hard to explain the automotive miracle that is the McLaren F1, a road car capable of reaching 386 kilometers per hour, making it the fastest production car in the world for over a decade, so fast that it held the top speed record from 1993 to 2005, untouched by Ferrari, Lamborghini, or Bugatti. A car so advanced that it featured a central driving position, gold-lined engine bay, and a naturally aspirated V12 that screamed to 7,500 RPM without a single turbocharger or supercharger. But get this, when Gordon Murray designed this car, he wasn't trying to build the fastest car in the world. He was trying to build the best driver's car ever made. The top speed? That was just a side effect of uncompromising engineering. The entire car was built around a simple philosophy: no compromises. Every single component had to justify its existence. If it didn't make the car faster, lighter, or better to drive, it was eliminated. This obsessive approach resulted in a car that weighed just 1,138 kilograms, despite having a 6.1-liter V12 engine. How on earth did they manage that? The answer lies in the most advanced carbon fiber monocoque ever created for a road car at that time. Carbon fiber composites had been used in Formula One for years, but never in a production vehicle to this extent. The McLaren F1's chassis was a single piece of carbon fiber, cured in an autoclave at precisely controlled temperatures and pressures. This wasn't just lightweight bodywork draped over a steel frame. This was the actual structure of the car, providing all the rigidity and crash protection needed while weighing a mere 107 kilograms. To put that in perspective, a typical steel chassis of the era weighed between 250 to 400 kilograms. The McLaren F1's carbon tub weighed less than 2 average adults, yet it was so rigid that the entire car had a torsional stiffness of 23,000 Newton-meters per degree. That's race car territory. But here's the crazy thing about that carbon monocoque. It wasn't just strong and light. It was also incredibly complex to manufacture. Each chassis took 3,000 man-hours to construct. The layup process alone required 28 individual panels of carbon fiber, each precisely oriented to handle specific load paths. The workers had to know exactly which direction the carbon weave needed to face for each section, because carbon fiber isn't uniformly strong in all directions. It's exceptionally strong along the fiber direction, but relatively weak perpendicular to it. So why did Gordon Murray insist on this central driving position? Wouldn't a conventional layout have been easier? The central driving position wasn't just a gimmick. It was fundamental to the car's design philosophy. By placing the driver in the center, Murray achieved perfect weight distribution and gave the driver the best possible sightlines. The 2 passenger seats were positioned slightly behind and to either side, creating a 3-seater configuration that had never been seen before in a supercar. This wasn't just about being different. This was about being optimal. The seating position also solved a critical packaging problem. In a conventional supercar, the driver sits offset to one side, which means the entire chassis must be wider to accommodate both the driver and the transmission tunnel. By centering the driver, Murray could make the car narrower, reducing frontal area and therefore aerodynamic drag. Every centimeter counted. And speaking of aerodynamics, the F1 achieved something remarkable. It generated downforce without any massive wings or spoilers. The entire underbody was designed as a diffuser, accelerating air beneath the car and creating a low-pressure zone that sucked the car to the road. At maximum speed, the F1 generated 680 kilograms of downforce, not as much as a dedicated race car, but more than enough for stability, and all of it achieved with minimal drag penalty. The drag coefficient was just 0.32. For comparison, most supercars of the era were around 0.38 to 0.42. This incredibly low drag, combined with the lightweight construction, meant the F1 needed less power to achieve higher speeds than its competitors. But of course, Murray didn't settle for less power. The engine was a masterpiece in its own right. BMW Motorsport was contracted to build a naturally aspirated V12 specifically for this car. The brief was simple but demanding. Create the world's best road car engine. No forced induction, no electronic nannies, just pure mechanical perfection. What they delivered was the S70-2, a 6,064 cubic centimeter V12 that produced 627 brake horsepower at 7,400 RPM and 651 Newton meters of torque at 5,600 RPM. These numbers might not sound astronomical by today's turbocharged standards. But remember, this was 1992, and this power came from an engine that would rev freely, predictably, and linearly from idle to redline. The engine itself weighed just 266 kilograms, including the flywheel and clutch. How did BMW achieve this? The block was made from aluminum alloy, as were the cylinder heads. Each cylinder had 4 valves, and the entire valve train used titanium components to reduce reciprocating mass. The connecting rods were forged titanium. The pistons were forged aluminum. Every rotating component was balanced to within 1 gram. But here's what really set this engine apart: the throttle response. With no turbochargers creating lag, and with such lightweight internal components, the engine responded to throttle inputs almost instantaneously. Press the accelerator, and the engine reacted within milliseconds. This was critical for a driver's car, where the connection between input and response creates the driving experience. However, an engine this powerful generates enormous heat. So how did they cool it? The F1's engine bay was lined with gold foil. Yes, actual gold. Now, you might think this was just extravagance, but gold is actually one of the most efficient heat reflectors known to materials science. The gold foil reflected radiant heat away from sensitive components and back toward the exhaust system and engine block, where it could be dissipated through the cooling system. Just 16 square feet of gold foil kept engine bay temperatures manageable and prevented heat from reaching the carbon fiber structure, which could weaken at sustained high temperatures. The cooling system itself was equally impressive. The radiators were positioned in the sides of the car, fed by NACA ducts in the bodywork. These ducts were designed to minimize drag while maximizing airflow. The entire cooling system could handle sustained high-speed running in ambient temperatures up to 40 degrees Celsius without any issues. So, if the engine could handle the heat and the chassis was strong enough, what actually limited the F1's top speed? The gearbox, specifically the gear ratios and the engine's redline. At maximum speed in top gear, the engine was turning at 7,300 RPM, just 200 RPM below its redline of 7,500 RPM. The engineers could have geared it taller to achieve even higher speeds, but that would have compromised acceleration and drivability. And remember, this wasn't just about top speed. This was about creating the ultimate driver's car. The gearbox itself was a work of art. A 6-speed manual transmission built by Weissman, weighing just 73 kilograms. It featured a magnesium alloy casing and used straight-cut gears for maximum efficiency. The shifter mechanism was connected directly to the gearbox with a rigid linkage, giving the driver precise mechanical feedback with every gear change. One huge question I had about the F1 was why they didn't use any driver aids. No traction control, no ABS, no power steering. Why strip away all these technologies that were becoming standard on much cheaper cars? The answer goes back to Gordon Murray's philosophy. No compromises in the pursuit of the ultimate driving experience. Electronic aids add weight, complexity, and most critically, they filter the communication between car and driver. Murray wanted the driver to feel everything. Every vibration from the road, every slip of the tire, every input transmitted directly and honestly. The lack of power steering meant the steering rack could be incredibly direct, just 2.25 turns lock to lock. This gave the car razor-sharp turn-in response. Yes, it made parking more difficult, but the F1 wasn't designed for parking. It was designed for driving at the absolute limit. The brakes were equally uncompromising. Ventilated carbon ceramic discs, 332 millimeters at the front and 305 millimeters at the rear. These were some of the first carbon ceramic brakes ever fitted to a production car. Carbon ceramic brakes can withstand temperatures exceeding 1,000 degrees Celsius without fading, and they weigh significantly less than steel discs. The front brakes alone saved 15 kilograms compared to conventional steel discs. But carbon ceramic brakes have a problem. They don't work well when cold. Below about 300 degrees Celsius, they provide poor initial bite. This made the F1 genuinely difficult to drive in normal traffic. The brakes felt wooden and unresponsive until they warmed up. This was yet another compromise that Murray refused to make. The brakes were optimized for performance, not convenience. Really, every single system on this car was optimized for performance without regard for conventional automotive norms. The fuel tanks were built into the carbon monocoque itself, using the structure as the tank walls. This was called a bag tank system. The fuel was held in flexible bladders that conformed to the shape of the chassis cavities. This saved weight by eliminating separate metal tanks and maximized the use of available space. The entire car carried 90 liters of fuel. At full throttle, the engine consumed fuel at a rate of approximately 48 liters per 100 kilometers. That meant at maximum attack, the F1 had a range of less than 200 kilometers. But fuel efficiency was never the goal. Performance was. Even then, without careful thermal management, this car would have destroyed itself. The exhaust system was made from Inconel, a nickel-chromium-based superalloy capable of withstanding temperatures exceeding 1,000 degrees Celsius. The exhaust gases exiting the engine were at approximately 850 degrees Celsius under full load. Regular stainless steel would have failed within hours at these temperatures and thermal cycling loads. The exhaust manifolds were also coated with ceramic thermal barrier coating to reduce radiant heat transfer to surrounding components. This same coating technology was used in Formula One and would later become standard in high-performance automotive applications. For this, we have to understand something called specific output. This is the amount of power an engine produces per liter of displacement. The McLaren F1's engine produced 103.4 brake horsepower per liter. That might not sound extraordinary by modern standards, where turbocharged engines regularly exceed 150 bhp per liter. But for a naturally aspirated engine in 1992, this was exceptional. The BMW M5 of the same era produced about 70 bhp per liter. Ferrari's V12 engines were producing around 85 bhp per liter. The F1's engine achieved this through high compression ratios, 10.5.1, variable valve timing on both intake and exhaust camshafts, and intake runners that were tuned to specific resonant frequencies to maximize volumetric efficiency at high RPM. But achieving high specific output isn't just about compression ratios and valve timing. It's about the entire breathing system of the engine. The intake manifold on the S72 was a masterpiece of fluid dynamics. Each of the 12 intake runners was precisely 300 millimeters long and 45 millimeters in diameter. These dimensions weren't arbitrary. They were calculated to create standing pressure waves at specific engine speeds. Here's how it works. When an intake valve closes, it creates a pressure wave that travels back up the intake runner, bounces off the plenum chamber, and travels back down. If timed correctly, this returning pressure wave arrives just as the intake valve opens again, effectively ramming additional air into the cylinder. This is called resonance tuning, and it can increase volumetric efficiency by 15 to 20% at the target RPM range. The BMW engineers tuned these runners to resonate between 5,000 and 7,000 RPM, which is exactly where the engine spent most of its time during spirited driving. Below 4,000 RPM, the engine felt relatively docile. Above 5,000 RPM, it came alive as the intake resonance kicked in, and the variable valve timing advanced the cam timing to its most aggressive profile. The variable valve timing system itself was hydraulically actuated, using engine oil pressure to rotate the camshaft relative to its drive gear. This allowed the valve overlap period to vary between conservative settings for low-speed drivability and aggressive settings for maximum power. At redline, the intake valves were opening 15 degrees before top dead center and closing 60 degrees after bottom dead center, creating massive overlap with the exhaust valves and allowing the momentum of the exhaust gases to help draw in the intake charge. The result was an engine that didn't just produce impressive peak numbers, but maintained strong power delivery across a wide RPM range. The torque curve was remarkably flat between 4,000 and 7,000 RPM, with over 600 Newton-meters available throughout this range. This broad power band made the car devastatingly fast in real-world driving. Not just on paper, these efforts helped extract maximum power from the engine. But the structure of the car still needed to handle enormous aerodynamic loads at high speeds. At 386 kilometers per hour, the aerodynamic forces on the car were immense. The total downforce of 680 kilograms was distributed roughly 40% to the front and 60% to the rear, keeping the car stable and planted. To understand just how significant these forces were, consider this. At top speed, the air pressure on the windscreen alone was equivalent to approximately 180 kilograms pushing against it. The doors experienced lateral forces exceeding 90 kilograms trying to push them outward. The entire carbon monocoque was flexing and deforming under these loads, though by only micrometers thanks to its incredible rigidity. the ground effect underbody was doing most of the heavy lifting when it came to generating downforce. The entire floor of the car was shaped as a venturi tunnel, with a relatively flat center section that gradually expanded toward the rear diffuser. As air accelerated through this constricting channel, its pressure dropped according to Bernoulli's principle, creating a low-pressure zone beneath the car. The diffuser at the rear was particularly sophisticated. It featured multiple channels that gradually expanded the airflow back to atmospheric pressure. This expansion had to be carefully controlled, because if the air separated from the diffuser surface, the downforce would collapse suddenly and unpredictably. The engineers used vortex generators along the diffuser edges to energize the boundary layer and keep the air attached to the surface even at extreme angles. The front of the car featured splitter elements that created a high-pressure zone above and a low-pressure zone below, effectively sucking the front end toward the ground. These splitters extended just 25 millimeters beyond the bodywork, but this small protrusion generated approximately 270 kilograms of downforce at maximum speed. But here's what's truly remarkable. The F1 achieved this with almost no active aerodynamic elements. There was no rear wing that deployed at speed, no active diffuser, just carefully sculpted bodywork and that ground effect underbody. The only movable aerodynamic element was the high downforce kit that could be fitted for track use, but this was optional. The standard car relied entirely on passive aerodynamics. This passive approach had enormous advantages. Active aerodynamic systems add weight, complexity, and potential failure points. They require motors, sensors, controllers, and wiring. The McLaren F1 had none of this. The aerodynamic balance was fixed and predictable. The driver always knew exactly how the car would behave at any given speed. However, this approach also meant the aerodynamic engineers had to get it absolutely perfect the first time. There were no adjustable wings to compensate for mistakes. The entire body shape had to work harmoniously from 0 to 386 kilometers per hour. Wind tunnel testing consumed over 800 hours during development, with engineers testing dozens of subtle variations in body contours to optimize the drag-to-downforce ratio. The side mirrors alone took 40 hours of wind tunnel time to perfect. Early designs created turbulent airflow that buffeted the side windows and created wind noise in the cabin. The final mirror design used a teardrop shape with a sharp trailing edge that cleanly separated the airflow, reducing turbulence by 70% and saving 3 drag counts overall. Titanium, the material we discussed earlier, was used extensively throughout the F1 despite being incredibly expensive. The entire exhaust system was titanium. The suspension components were titanium. The brake caliper mounting points were titanium. The fasteners were titanium.
And it's the world's first titanium toolkit.
This material was chosen because it offered the best strength-to-weight ratio while being able to withstand high temperatures without losing structural integrity. But the use of titanium presented significant manufacturing challenges. Titanium work hardens rapidly when machined, meaning cutting tools would wear out incredibly quickly. Special carbide tooling had to be used, and cutting speeds had to be reduced by 60% compared to steel. This made every titanium component time-consuming and expensive to produce. Welding titanium was even more challenging. Titanium reacts with oxygen, nitrogen, and hydrogen at temperatures above 400 degrees Celsius, becoming brittle and weak. Every titanium weld had to be performed in an argon-shielded environment to prevent atmospheric contamination. The welders working on the F1's exhaust system worked inside argon-purged chambers, essentially welding in a controlled atmosphere. The suspension wishbones were forged from titanium billets, then CNC machined to their final shape. Each wishbone weighed just 720 grams, but could withstand loads exceeding 15,000 newtons without permanent deformation. Comparable steel wishbones would have weighed 2.1 kilograms each. Across all 4 corners of the suspension, this saved nearly 11 kilograms of unsprung weight. Unsprung weight is particularly critical in suspension design because it affects how quickly the suspension can respond to road irregularities. Lower unsprung weight means better tire contact with the road, improved handling, and better ride quality. The F1's total unsprung weight was just 118 kilograms across all 4 corners, about 40% less than comparable supercars of the era. But titanium too has its limits, and for some components, the engineers needed something even more exotic. The engine's connecting rods, as mentioned, were forged titanium, but they were also surface treated with a process called shot peening. This involves bombarding the surface with tiny spherical projectiles, creating beneficial compressive stresses that significantly increase fatigue life. The shot peening process used ceramic beads traveling at approximately 90 meters per second. These beads impacted the surface of the connecting rod thousands of times, creating a compressive stress layer approximately 0.3 millimeters deep. This compressive stress prevented crack initiation and propagation, which is the primary failure mode for highly stressed components that undergo millions of load cycles. Each connecting rod in the F1's engine experienced peak loads of approximately 45,000 newtons during every combustion cycle. At 7,400 RPM, that's 3,700 load cycles per minute. Over the engine's service life of approximately 160,000 kilometers, each connecting rod would experience over 740 million load cycles. Without shot peening, fatigue cracks would have formed within 100,000 kilometers. The crankshaft was another engineering marvel. It was forged from a special steel alloy containing chromium, molybdenum, and vanadium for strength, then nitrided to harden the surface. Nitriding involves exposing the steel to nitrogen gas at 525 degrees Celsius for 72 hours, creating an incredibly hard surface layer of iron nitride compounds. This surface was harder than the ceramic beads in the shot peening process, with a hardness of 68 on the Rockwell C scale. The crankshaft weighed 28.4 kilograms and was balanced to tolerances of 5 grams. This level of balance was critical because at 7,400 RPM, even a 10-gram imbalance would create vibrations that could damage engine mounts and create unacceptable noise, vibration, and harshness in the cabin. Today, engineers have made huge strides in material science and hybrid powertrains. The McLaren F1 used no hybrid technology, no turbochargers, no active suspension. The manufacturing techniques needed to mass-produce carbon fiber tubs did not yet exist at scale, but that has changed. Modern carbon fiber manufacturing uses automated fiber placement machines that can lay down carbon tape with tolerances of 0.1 millimeters.